So you've probably played around with ChatGPT, right? You've seen it write a poem or debug some code, and you've had that moment of, wait, how is that even possible? Well, the answer isn't magic. It's actually a specific and frankly brilliant piece of engineering. In this explainer, we're going to pull back the curtain and show you how it all really works. Let's dive in.
I mean, that's the core mystery, isn't it? How could a machine, just a bunch of circuits in code, get the nuance, the context, and even the creativity of human language? It feels like it shouldn't work. But the answer lies in a revolutionary design that completely changed the game.
Okay, so to really appreciate this breakthrough, we first have to understand the massive problem that it solved. For years and years, AI models had this huge fundamental blind spot. They were terrible with memory and context.
I want you to imagine reading a book, but you can only see one word at a time. And by the time you get to the end of a long sentence, you've completely forgotten how it started. That was basically the reality for older models, like what we call recurrent neural networks, or RNNs. They processed text in a straight line, which was not only super slow, but made it almost impossible to connect ideas across a big paragraph.
And here, the difference is it's night and day. On the left, you've got the old way, just crawling along, word by word. But on the right, that's the game changer, the transformer. It doesn't read in a line. It looks at every single word in the sentence all at once. This parallel approach isn't just way faster. It lets the model see the whole picture, to understand how every word relates to every other word, no matter how far apart they are.
Right, so this brings us to the hero of our story, the transformer architecture. It came out of a 2017 paper called Attention is All You Need. Great title, by the way. And it wasn't just a small improvement. It was a total reimagining of how a machine could process language.
And the absolute core of that reimagining is this concept called the attention mechanism. The easiest way to think about it is like the model's superpower, its ability to focus. For any word it's looking at, the attention mechanism scans the whole sentence and gives a relevance score to every other word. It's literally how the model learns what to pay attention to.
Take a look at this really simple sentence. As a human, you instantly, without even thinking, know what it refers to. But for a machine, solving this little pronoun puzzle is actually a massive challenge, and it's exactly where the older models would just fall flat. So this is the million-dollar question that the attention mechanism was built to solve. How does it figure out that it connects all the way back to animal and not the word street, which is actually closer but totally wrong?
Well, the process works kind of like a detective investigation. First up, the word it sends out a query, basically asking, hey, who in this sentence am I connected to? Then every other word presents its key, which is like its identity card. Hi, I'm animal. I'm street. In step 3, the model calculates a relevant score between the query from it and every single key. And bingo, it finds a super high score between it and animal. Finally, the word animal provides its value, its actual meaning, back to it, which locks in that connection. And this happens for every word at the same time, creating this incredibly rich map of how everything is related.
All right, so that's the engine under the hood. Now let's see how it's actually being used out in the real world. You see, the transformer is the blueprint, but different teams build their models with their own little tweaks. And the two most famous architectures today are, of course, OpenAI's GPT series and Meta's Llama models.
Before we compare them, it helps to know one quick technical term: rope. Because transformers look at all the words at once, they need a way to keep track of word order, right? Otherwise, the dog bit the man is the same as the man bit the dog. Rope is a really clever and efficient method that Llama uses to encode the relative position of words, and it's especially good for handling really long stretches of text.
So when we put them side by side, you can really see the different engineering choices. Where GPT learns the absolute position of a word, like this is word number 5, Llama uses that more modern rope we just talked about, so it understands words in relation to each other. They also use different activation functions. Those are kind of like the on-off switches for their neurons. And this is a big one. Llama uses a more efficient type of attention called grouped query attention, which helps it run faster with less computing power. And of course, the most fundamental difference of all, GPT is a closed source black box, while Llama's open weights approach lets researchers pop the hood and see exactly what's going on. So what this all boils down to are two pretty different philosophies. Historically, OpenAI and GPT have been all about pushing the limits of scale. Just more parameters, more data, more power. Meta, with Llama, has been the champion of efficiency. They're trying to prove that you can get amazing performance with smarter, higher quality training data, all while keeping things open for the community. So, why does any of this technical stuff matter to you, the person just trying to use these tools? Well, it's because these architectural choices directly lead to the amazing abilities and, yeah, the really frustrating limitations that we all run into every day. Let's start with scale. Just look at this number. GPT-3, the model that really kicked off this whole AI boom, has 175 billion parameters. A parameter is essentially a tiny knob that the model tunes during training to learn a pattern. And the new models have way, way more. This kind of insane scale doesn't just make the models better, it unlocks brand new skills. And this is where things get kinda wild. These new skills are called emergent abilities. Things like few-shot learning, where a model can learn a new task from just a couple of examples you give it, or chain of thought reasoning, where it actually breaks down a complex problem step by step to find the answer. The crazy part is nobody explicitly programmed these skills into the AI. They just emerged as a byproduct of the models getting so massive. But the architecture also has some deep inherent flaws. The most famous one, of course, is hallucination. It is so important to remember that at its heart, an LLM is a next word prediction engine. Its entire job is to generate what is plausible, not what is true. It doesn't have a little fact checker in its brain. It is just an unbelievably sophisticated pattern matcher. So you can think of this as a quick owner's manual. First, it can and will invent facts. Second, it has a limited memory or context window, so in a really long conversation, it can forget what you talked about at the beginning. Third, it's going to reflect the biases from its training data. And, maybe most importantly, you have to remember, it is a world-class mimic, not a mind. It is incredible at pattern matching, but it doesn't understand things the way a person does.
And that really leaves us with the big, fascinating question. We've built these incredible machines that can mimic human language with shocking fluency. They're powerful, they're useful, and they're built on this revolutionary architecture. But there's still a huge gap between mimicking intelligence and actually possessing it. So as we look to the future, the biggest challenge isn't just about making these models bigger or faster. It's about discovering what it will take for them to finally make that leap from prediction to true understanding.